Hello, I am Tyler Linder, and this is my Lab 4 assignment. The title of this lab is Magnetic Braking with Faraday. So to introduce this lab, the purpose of it is to observe a magnet falling through a conductive tube of aluminum foil. Then we must collect and analyze observational data from the experiment. Once that is done, we will create a computational model of the magnet tube interaction that we just did. And then once that is finished, we can compare the observational data and the computational data to find some similarities and differences between the two. The fundamental physical properties of this lab is Faraday's law, Lenz's law, magnetic flux, and Newton's second law. So for the experiment, I have listed the materials and the procedure for you to do on your own. It is very simple, and I hope you guys have a fun time doing the experiment. So after completing the experiment, you must observe the tube length, foil tube width, foil tube inner radius, magnet mass, and the magnitude of the magnetic dipole moment from Lab 1. For my experiment, the data that I collected from each trial is that the first trial, the magnet fell within half a second, and then during the second through fifth trial, they were all less than half a second. The average time for each trial was 0.38 seconds. So here we have our computational code to set up the computational model of the experiment that we just completed. You can find this complete code using the link in the description. A few of the most important codes that you need are the physical constants, and then a code creating the tube of aluminum foil, and then also the code creating the bar magnet. For the foil and the bar magnet, it is the same exact things that we found in our observed data. Moving forward, we must create two functions. And before that, we must also set some initial conditions for our functions. The first one calculates the magnetic field of the bar magnet, and the second one calculates the magnetic flux. After that, we must create a simulation loop for the magnet falling through the tube. This code functions to check if the magnet is in the tube first, and then it iterates it across rings to find the net magnetic force on the magnet. Once that is complete, the magnet's acceleration is found, and then it changes the magnet's position accordingly. And then after that, the magnet's position and velocity versus time is plotted on the graph. So here's my computational model after running the code. It starts off as a blue object at the top of the tube, and then it falls and travels down through the tube, turning red. Once it reaches the bottom, the simulation stops. And then once that is complete, we have our printed results. On the left side, we have our velocity versus time graph, representing the speed over time of the magnet falling through the tube. And then to the right, we have our time of the magnet falling through the tube in seconds. So to compare the two types of data, they are both similar in tube size, magnet size, and magnitude of magnetic dipole moment. The difference between the two are the average time it took for the magnet to fall through the tube. Of course, for our observed time, we got 0.38 seconds. And then for the computational time, we got 0.322 seconds. In conclusion, we have two what-if statements. The first one is asking, if the resistivity of the conductor were reduced nearly to zero, how would the dynamics of the falling magnet change? Well, my answer to that is that the magnetic force increases in magnitude, causing the magnet to fall slower. Then the force grows because the current and the resistance are inversely proportional. The second what-if statement reads, if holes or slot were cut into the tube, how would this affect the ring currents in the model? My answer to this one is, the magnet will fall faster as the current is decreasing. The induced current rings would be interrupted at every slot, and the magnetic force on the magnet would be weakened. Thank you for this time and for listening to my presentation.